Okay, so in the previous video, we talked about different states or different phases of matter. In this one, we want to know why. Why do these different states of matter, different phases of matter, have the properties that they have, right? So that's our question. We're going to start with solids again. I've got the same picture here of crystals that we used in the last video. Same picture, there's some crystals there. And then I kind of just indicated that we're zooming in. It's obviously not this whole chunk that I'm zooming in on, but anyway, the image is there just to show you the zoom. So we're zooming in, and we're looking at the crystal structure of the atoms in that crystal. So they look something like this, all right? They're going to pack together as tightly as possible into this neat crystal arrangement, try to minimize the empty space in there, and get all of these atoms as close together as possible. And the question is why? Why do solids do that? Why do they want to pack in all close together? What makes them want to do that? And the reason is sort of summarized here. They have a very strong attraction. So their molecules are basically locked in place. So why are they attracted strongly? Well, without getting into too much detail that you don't really need to know about, here's the short version. In this case, in an ionic solid, a crystal structure like this, what you have here is some plus ions represented by the green and some minus ions represented by the purples. All right, so if these are plus and these guys are minus, they're going to be attracted to each other very strongly. They have a very strong attraction, so they want to get as close together as possible. And they also don't really want to be right next to the other things that have the same charge they do. So that's why there is a purple in between every green. The greens are both plus. Pluses are not attracted to each other. They're repelled from each other. So all of these guys want to be next to a minus. This guy wants minuses all around him. So that's how it's going to work. Each of these guys has, each of the green ones has purples all around it, and each of the purples has green ones all around it. So there's very strong attractive forces when there's minuses next to pluses, so they want to get as close together as they can. So that's why, and it's not always, not every solid is ionic like this, but the reason that every solid is in solid form is because of the strong force attracting them to each other. They're being pulled together, right? So they want to get as close together as possible. All right. That's basic. That's the basics for solids. Let's move on to liquids. All right, liquids. So what's going on in liquids then? Well, as you can see, liquids, the molecules are more able to flow past each other. They're not locked in place. They're a little bit more fluid. They're still close together, but not as close as a solid usually. They're a little bit further apart. They're a little bit more free to bounce around. They're definitely free to flow along past each other. And why is this? Why are they locked in place in a solid, but they're more capable of flowing in a liquid? And the answer for that is that there's less, the attractive forces between these molecules is less. So there's not as much attraction between them. They're more able to flow. Or, alternatively, there's another force at work, right? Maybe they have essentially the same amount of attraction for each other as they had in their solid form, all right? But here's the trick. They have more heat energy, right? Maybe these guys have more energy of motion. They're moving faster. They have more energy. They have more heat. For example, in liquid, if this was water, all right, as opposed to ice, in ice, there is less heat energy in the H2O, right? So if there's less heat energy, then there's less motion, right? So they're not moving as much. They're moving slower. The molecules are moving slower in ice, so the attractive forces are able to overcome the motion of those molecules, and they're held in place. But in a liquid, right? So in a liquid like this, if these represent molecules of H2O, then these molecules have enough heat energy, enough energy of motion, they have enough kinetic energy that they can overcome some of the attraction to their neighboring particles, right? So not all of the attraction, but they can overcome some of the attraction. So they are no longer held rigidly in place by their attraction for each other. They have enough energy enough energy that they can bounce around, they can move, right? They can move past each other, they can slide around and all interchange places and stuff, right? And we're like crazy in there. But not enough to be bouncing and filling up the container and turning into steam, right? So they're somewhere in between. They have enough energy to flow, but not enough energy to like separate into a gas. So that's the basic idea of a liquid. They have moderate net attractive forces, right? Moderate attractive forces. So their molecules are close together, but they're not locked in place. All right. So possibly this could be, why is this one a liquid where something else is a solid? Well, if they're both at the same temperature, right? Say that you have a crystal that's at the same temperature as this, and then you have this, right? This water, we'll call it water. Then why at the same temperature, so they have the same heat energy, why are they one liquid and one solid? And the answer to that is that this has less attraction among its molecules than the solid crystal does at the same temperature, right? So there's more attraction in the crystal. It's not able to overcome, the atoms in the crystal are not able to overcome their attractive forces. They would need a lot more heat energy in order to overcome their attraction and then be able to flow past each other. It is possible you can make a salt into a liquid, but it gets really, really hot when you do that, all right? Because the attraction of those ions is just so strong. Okay, cool. Then we have gases. Now again, here we've got a gas, and this one's also at room temperature. So we've gotten 3 examples, a crystal, a liquid, and a gas, all basically at room temperature. And again, why is one a solid, one is a liquid, one's a gas? And that's because of the attraction between the atoms or molecules that are in here, right? So in this case, this gas, the attraction of those molecules for each other is really small. It's very weak at room temperature, right? So the weak attractive forces have no chance of overcoming the motion of these gas molecules. So the moving gas molecules basically just go wherever they want. They bounce all over the place. They hit each other. They hit the sides of the container. It's like a crazy mosh pit party, whatever you want to think of, just bouncing around like crazy in there, all kinds of energy. There's a lot of space in between the particles. There's essentially no attractive force, or very, very small attractive force of any of these atoms for any of these other atoms. So they're just moving really quickly, they're bouncing off each other, they're going all over, and they are not attracted to each other, at least not enough to clump together. So in a gas like this, the attractive forces are very weak compared to the kinetic energy that the things have. So basically the molecules are just free to bounce all around anywhere inside the container. Or if they're not in a container, they're just going to fill up all of the available space. Bam, all of it. Take up all of it. All right. So here's a summary of what we've been talking about. In a solid, you've got your atoms all close together, or molecules. They're all clumped up really close together and tight, and they're attracted very strongly to each other. Possibly they don't have very much energy of motion, not much kinetic energy. There's not a whole lot of heat energy in there, possibly. So in that case, they are in solid form. Now this is the same thing here as we have here, right? You can tell it's the same molecule. So why is this one liquid? And the answer to that, if it's the same molecule as you've got there, the answer to this is that it's gotten heat energy. The heat has increased. So more heat has been added to those. More heat energy there. So if there's more heat, then they are going to be able to overcome some of their attractive forces, and they will then spread out more. Not totally, but they'll spread out more. So then, the question, if you've got a gas of the same molecule, what's happening there? And basically the answer is you've got even more heat. I'm just going to go ahead and write that in because it's fun. Even more heat. All right, so if you get even more heat, then that's going to be enough to break all of the attractive forces, essentially. And there's enough kinetic energy in there, there's enough heat energy, thermal energy added to these particles they're moving fast enough now that the attractive forces cannot hold them together anymore, and they spread out and fill up all of the space. All right, so that's the summary of that idea, and then here you can see it a little bit more clearly in terms of heat and pressure changes. So this diagram incorporates everything we've been talking about, basically, and you can look at that more if you like by pausing the video. I'm not going to talk about it in detail. All right, so there you go. That's basically the molecular theory of matter, and the theory of what's going on with atoms and molecules at that really small scale, and what's going on there that makes them solids, liquids, and gases, and what makes any particular compound or element into a solid, liquid, or gas at a specific temperature. It has to do with the balance of the kinetic energy, all right, the energy of the motion of those molecules, the heat energy, all right? So it's the balance of that energy versus the attractive forces. And if the attractive forces are strong enough, they will hold those molecules together, or atoms. And if those attractive forces are weaker than the kinetic energy, then basically they're not going to be held together solidly. They might be either a liquid or a gas. All right? Cool. I hope that was clear.